Hello everyone, myself Pradeep. Today I am here to present a topic of convolution operations. Introduction to convolution. Convolution is a mathematical operation used in various fields, including image processing and neural network. It involves the combination of two functions to produce a third function, highlighting shared features. In deep learning, convolution is primarily applied convolution neural network called as CNN for processing image data. Operations in convolution. The convolution operation combines an input image with a filter or kernel to produce an output feature map. Mathematically, convolution can be represented as the integral of the product of two functions. In discrete terms, it involves sliding the kernel across the input and calculating the weighted sum of each position. Convolution layers in CNS. Convolution layers are essential component of CNN architecture designed to capture specific hierarchies. Each layer learns to detect specific features like edge, texture, or pattern through filters. Stacking multiple convolution layers allows the neural network to learn increasingly complex representation. Filters and kernels. Filters, also known as kernels, are small matrices that slide over the input data during the convolution process. Each filter is responsible for detecting particular feature in the input, such as a vertical or horizontal edges. The size of the filter can significantly affect the output, and it's typically chosen based on the specific problem domain. Padding in convolution. Padding involves adding extra pixel around the input image to control the spatial dimension of the output. It helps preserve the spatial information and allows the use of smaller filter without losing data at the edges. There are different types of padding, include valid, same and full, each affecting the output sizes. Stride in convolution. Stride refers to the number of pixels by which the filter moves across the input image. A large stride results in small output feature map, reducing computation and memory requirements. Adjusting the stride can help control the level of downscaling and the granularity of feature extraction. Activation functions of CNNs. After convolution, an activation function is often applied to introduce non-linearity into the model. Common activation functions include ReLU, sigmoid, and tan, each with distinct properties. Non-linearity allows the network to learn complex patterns in the data that a linear model cannot capture. Downsampling techniques. Downsampling reduces the spatial dimension of the feature maps, often improving computational efficiency. Common downsampling techniques include max pooling, average pooling, and straight convolution. Each method retains essential features while discarding less significant informations. Convolution variants. There are several variants of convolution that address specific needs such as dilated and depthwise separable convolution. Dilated convolution expands the receptive field without increasing the number of parameters. Depthwise separable convolution breaks down standard convolution into depthwise and pointwise operation for efficiency. Convolution neural network architecture. CNN is typically consists of alternating convolution and polling layers, followed by full connected layers. This architecture enables the neural network to learn hierarchical representation of the input data. The final layer usually involves softmax activation for classification tasks. Training CNS with backpropagation. CNS are trained using backpropagation where gradients are computed to update the weight of the filters. The loss function quantities, the difference between predicted and actual output, guiding the optimizing process. Techniques like dropout and batch normalization are often employed to improve training stability and performance. Transfer learning allows the reuse of pre-trained models on new tasks, saving time and computational resources. It is particularly useful when limited labeled data is available for training. Fine-tuning pre-trained models can lead to improved performance on specific applications. Applications of convolution in deep learning. Convolution operations are widely used in computer vision tasks such as image classification and object detection. They also find application in natural language processing, particularly for text classification and analysis. Other fields include medical imaging, video recognition, and autonomous driving. Challenges in convolution network. Despite their success, CNS can struggle with overfitting, especially with small dataset. Computational expense and long training times can be significant challenge when scaling up models. Additionally, CNNs may not generalize well to unseen data if not properly regularized. Features direction in convolution research. Feature research in convolution may focus on improving model efficiency and reducing computational overhead. Technique like neural architecture search aim to automate the design of optimal convolution structure. Exploring unsupervised and self-supervised learning approach can also enhance feature extraction capabilities. CNNs are employed in facial recognition system enable accurate identification in security applications. They are used in autonomous vehicle to detect and classify objects on the road in real time. Additionally, CNN assists in diagnosing disease from medical imaging and data improving health center outcomes. Well-known CNN architectures include LENet, AlexaNet, VGG, RESNet, and Inception. Each architecture introduced innovation that improved performance and efficiency in specific tasks. Understanding this architecture helps in selecting appropriate models for various applications. Tools and framework for CNNs. Several deep learning frameworks such as TensorFlow, PyTorch, and Keras facilitate building CNNs. These tools provide pre-built layers and models, making it easier to implement complex architecture. They also support GPU acceleration, significantly speeding up training and interface process. Conclusion. The conclusion operation is a cornerstone of deep learning, particularly in image processing. Its ability to detect and learn feature has revolutionized various applications across multiple domains. Ongoing research and advancement continue to enhance the capabilities and efficiency of convolution neural networks.